Hey, welcome back to Fat Mama Physics. In this video, we're going to talk about examples involving Feynman diagrams, a very strong representation, a visual representation of a particle-particle interaction, showing their probabilities so that we can figure out the probability of a reaction happening and compare that with our data that we collect. Okay, so let's take a look at some examples. I'm just going to quickly go over these general rules. Hopefully you have seen them or are aware of them already. So very quickly, notice this, in the Feynman diagram, you'll notice that there are two axes. You have an axis for time and you have an axis for space. Usually the time is going to progress from the left to the right, and in some cases it might progress from down to up. So before any time you start a Feynman diagram, you need to check the axes if they are given to you. So you might notice different kinds of lines. So if you have an arrow pointing towards a junction, so moving forward in time, it represents a fermion, which either is a quark or is a lepton. But if you have, say, an arrow that is leaving or entering a junction that is pointing backwards, such as this guy over here, that's not representing the particle going backwards. This is the particle. It's just another way for us to represent an antiparticle. So an antiparticle, or in this case, our fermions, antiquark, or could be an antilepton. Then you might notice lines that are wavy, or they look a little bit different than your arrows. So these represent the exchange particles or gauge bosons. So you have we have wavy lines, which most of the time we use for W and Z bosons. So that's either W plus, W minus, and Z 0 or neutral Z. With photons, usually we use wavy lines as well, and sometimes on the IB exam they like to use both, but usually they are labeled, so that's something to look for. I know, confusing, right? Here we have a curly one. This one is a gluon mediating the strong nuclear force, okay? So notice that each of these mediate a different force. Photons for electromagnetic, the W and the Z bosons for your weak interactions, and gluons your strong nuclear interactions. At every junction, notice that you have an incoming particle, an outgoing particle representing the past and representing the future. And also at every junction, you might notice that there is some sort of a mediating particle or some exchange particle in the process. So notice that vertices may be connected with these exchange particles to show an interaction happening. At every junction, all conservation laws apply. Okay, so hopefully you know all your conservation laws, including baryon number, lepton number, charge conservation, strangeness. Well, strangeness you can look at in terms of weak interaction or not. So you do have all your conservation rules that apply. Okay, so I think we should get started with some examples. But before that, just hopefully you've seen a little bit of different kinds of examples. So hopefully you've seen this page. A couple of interesting characteristics. So I know all of this, it's very, it's a lot to take in all at once. So here are some general examples, our general kind of, I say categories of reactions. For example, this one here, you have an incoming particle and then something goes out. Usually it's a different one, or is this the same one? If it's regardless of what that one is, this represents a type of decay. So some sort of decay is happening in which an exchange particle leaves and it decays further into a particle and an antiparticle. So that's kind of how an exchange particle leaves, and to mediate that decay. There are ones where they come together. So sometimes you might have an exchange particle turning into a particle-antiparticle, or you have a particle-antiparticle combining to annihilating to become some sort of energy or some sort of a photon, or it can be other exchange particles. So they come together, they meet at a point, and then they become something else. So that's two types. You got a decay, you got annihilation happening here. Here we have an interesting one where you have an extron and positron annihilating to produce two photons. So there's an interaction happening there. And notice that we need two vertices to represent the two different, since there are two photons that are produced, okay? So hopefully you have a bit of a couple examples to give you an idea. Decay and annihilation are your common ones. So, pair production, annihilation, and decay. So in this video, I'm going to mainly go over the beta plus as well as the beta minus decay, and to look at it and draw the Feynman diagram for them, okay? So let's start with a beta decay equation. But this, but we're working with subatomic particles. We are working with whatever is changing. Whatever is not changing, like the rest of the nucleus, we don't really care about, because we want to look at the a very small scale. Okay, so for a beta decay, essentially what is happening is that you have a proton that decays into a neutron and a positron with the antineutrino. So that is what we will be doing. We'll be looking at just the photons and the neutrons instead of the entire radioactive isotopes. So generally we have a photon, which we'll represent with a P. Photon has a atomic mass of 1, atomic number of 1 with a positive 1 charge. So a proton becomes a neutron with atomic mass of 1 but no charge. A positron is created, which is the antiparticle of an electron. It has no atomic mass but has a positive 1 charge. And we also know that an electron neutrino is produced with no charge and very little mass. Okay, so let me get rid of these lines here so it doesn't clog this up. Okay, so this is essentially what is happening, and we want to break this one down into the individual steps. So in a Feynman diagram, notice that usually we like to work with the constituents of particles. So if we're talking about protons and neutrons, we want to work with the quarks to see what is happening down at the fermion level. So let's figure it out. Inside the nucleus, we know that a proton is decaying into a neutron as well as the other parts. And we know that in a proton is composed of 3 quarks. It's composed of an up quark, and a down quark. How do you know that? Well, you have to look at the charges. It's hopefully it is common knowledge, but we can always check with the charges. And if you want to check the charges on any quark, you can go to your data table. So here I have your data table for the appropriate section. Notice that all of your quarks on the top line, this is the up charm top, have a charge of 2/3 of an elementary charge. The ones on the bottom have a negative 1/3 charge. Of course, the antiparticle, the charge will swap. So for a proton, an up quark, and a down quark is going to produce a positive 2/3 plus another positive 2/3 plus a minus 1/3. And if we add them all together, that's going to give us a net positive 1 charge. Okay, so that's how you can work out the charge of a proton. But hopefully you know at this point that it's composed of a up, and a down quark. For a neutron, it is composed of a up, down, and another down quark. Also should be common knowledge that at this point, if we can do a check, so up, down, down, this is 2/3, minus 1/3, minus another 1/3 gives us a net charge of 0. Okay, so the charges work for both a proton and a neutron. Whenever you're looking at a Feynman diagram, we always want to figure out the path that involves the least number of possible interactions, because it will hide the highest probability of it happening. So when we look at a proton to a neutron, we want to figure out what is happening with the quarks. And we want to look at what is the least amount of change that needs to happen in order for up-up-down quark to become an up-down-down quark. And immediately, we know that we want to figure out what is... we look at what is similar between our reactants and our products. We notice the up quark here, the down quark and the down quark. These are all the same. So the only thing that needs to happen, or the least thing that needs to happen, at least an up quark turns into a down quark. So this is the minimum processes that needs to happen. So here we have an up quark is going to turn into a down quark. I'm just using symbols here to represent that. Which exchange particle boson would be involved in this case? So we know that in a decay, in any decay reaction, decay reactions are usually mediated by the weak force, not the strong force, not the electromagnetic force, the weak force. And then since it is mediated by the weak force, we know either it's a W boson or a Z zero boson. So it's either one of these three bosons. So to figure out which one it is, we would have to think about what the products are, and also we probably have to finish our Feynman diagram to give us a better understanding of which exchange boson or which charge is needed. At this point, we probably are going to rule out the neutral one because we're going to get a negative charge from a positive charge. But we'll take a look what that looks like. First of all, we're going to have a proton here. And notice it shows us that the up quarks and down quarks don't change. The only thing that's changing is an up quark to a down quark. And this product here is a neutron. So whenever doing the Feynman diagram, I find it helpful just to jot down notes for myself to figure out what the charges are. So for example, this up quark is a positive 2/3. This one is a minus 1/3 charge. We also know that these two products produced are going to be your positron and your antineutrino. So we can put these in right now. So we have a positron, which I'm going to write E+, and this guy is an antiparticle. So remember, antiparticles, they have their arrows moving backwards. Doesn't mean they're moving backwards in time. It's just a way for us to model or to show that this is an antiparticle on a drawing, on a diagram. And the other particle here is an electron neutrino, which is not an antiparticle, so we're going to have the arrows moving forward in time. So based off of these interactions, we know that at the end, we're going to, whatever is mediating this decay is going to give us a minus 1/3 charge, and also is going to produce a positive charge. So whatever is leaving here, remember, a charge has to be conserved. The easiest way to figure this one out is just to look at this vertex right there. So whatever is coming in is going to produce a positive +1 charge. And there's a 0 charge on the electron neutrino. So whatever is coming in has to have a positive charge, and that can only be mediated by the positive boson. Okay, so W plus boson. And we can just use this to check here. We have a +2/3 coming in, it loses a +1 charge into the W plus boson, and yes, it will give us a -1/3 charge. So what that is 2/3 is equal to +1 minus 1/3. Okay, so that's our charge conservation that works. Therefore, this mediator boson exchange particle has to be W plus. Okay, so there we go. There's the beta plus decay equation. I highly recommend you fully understand how this decay works and to be able to fully draw the Feynman diagram yourself. Speaking of which, let's go ahead and work out the weak interaction vertex diagram for a beta minus decay. The first thing I would ever do when we're starting off with Feynman diagram is to actually write the equation down itself if the question does not provide it. For beta minus decay, we know very well this is the opposite of a beta plus plus decay. This is a neutron turning into a proton plus a beta minus particle, or essentially an electron and its anti-neutrino, like that. Okay, so if we just fill out these boxes over here, actually no, before that, let's take a look at the quarks that are involved. So usually getting an equation would be the first step. The next step is to break all of the particles down if they can be broken down. A neutron is going to have an up, down, down quark. Proton's going to have an up, up, down quark. So again, it looks like a down quark is going to get converted into an up quark. And because of that, let's fill in the rest of the table here. So here we have a down quark from a neutron will get converted to an up quark. And everything else looks like it's gonna have to, there's no other changes. So essentially, this mediating boson is going to produce the this pair, this particle-antiparticle pair. And this one here has to be the electron, which is E minus. And since this guy is the particle, this one, the anti-neutrino is going to be an antiparticle, so I'm going to draw the arrows in the backwards direction, just like that. And the last but not least, we need to figure out what the boson that is involved in this decay. We know that at this vertex moving forward, we're going to get a -1 charge plus 0. So this mediating boson has to be W minus that is coming in. So a down quark has a -1/3. So we're just going to do the check for the conservation of charge at that point. So a -1/3 is going to become a -1. And then an up quark is a positive 2/3 charge. So -1 plus positive 2/3. This is going to give us -1/3. So charge conservation checks out. So the mediating particle, the exchange particle here is the W minus boson. And it kind of works hand in hand with the type of decay. Beta's minus decay for W minus, and beta plus, we have the W plus boson mediating that. Okay, so there you go. These are the two the beta decay equations. I highly recommend that you know how to do these very well. Okay, otherwise stay tuned for the next few videos. I am going to be doing more examples on the Feynman diagram, and always try to get more practice with Feynman diagrams to work out your own system. So I wish you the best of luck, and I thank you for watching. Fan Mama Physics signing out.